Once the 369 is installed, it must be configured using either the keypad or PC-based software. In this section, we will use the Intervista 369 setup software to configure the relay to protect a motor in a simple across-the-line start application. This example is intended for teaching purposes only. It is recommended that a qualified protection engineer determine the settings for your motor protective relaying application. The first step in using the setup program is to configure the communications to allow us to talk to the relay. We will do this by selecting the Device Setup button located above the online window on the left side of the screen. In the window that appears, you will see the panel on the left-hand side showing the text, "Please add a site." This indicates that no sites or devices have been set up for communications. First, we need to add the site that will contain the relay. Press the Add Site button found at the top of the window. A new site will be added with the default name, New Site 1. To change the name of the site, click on the Site Name field and type in a new name. Next, we will add all of the devices that we want to be found in that site. Highlight our site by clicking on it and press the Add Device button. Two things should now have occurred. The name of our site would have changed, and a new device will be added to the site with a default name, New Device 1. We now need to configure that newly created device. In the panel on the right, click on the Device Name field. Type in a new name that describes that relay. Open the pull-down menu. Because we are configuring to communicate with an RS-232 serial cable, we will select Serial from the menu. Several new fields will appear in the area below. The Modbus slave address is used to identify specific devices for communicating on the network. When communicating through the front port, there is only one device on the network. Therefore, there is no risk of communicating with the wrong device. For this reason, we can leave the Modbus slave address to the default of 1. In the COM port field, select the communication port of your computer that the serial cable is connected to. The COM port that we are using is COM1. Therefore, we will leave this at the default. The baud rate has been set to 9600. The order code and firmware version can be read from the relay itself to fill in the last two fields. Press the Read Order Code button. Press the OK button. Once the device setup has been completed, you will see the name of the site you have created in the device window. By opening this menu, you will see the name of the device that was set up for communications. Opening this menu further, you will see the menu structure for the relay itself. This is one of two methods that can be used to view the settings and actual values that are present in the relay. By double-clicking on the settings, you will see the available settings for the basic operations of the relay. By double-clicking on a settings menu, you will see the specific settings for that function. The second method for viewing the settings in the relay is to click on the Set Points drop-down menu. This will show a list of all settings pages within the relay. Please note that the grouping under the Set Point drop-down menu matches the structure of the set point pages found in the relay. If you familiarize yourself with the menu structure by using the PC program or the keypad, the transition to the other interface will be very simple. Customizing the appearance of the setup program can make it easier to navigate the settings of the relay. For instance, the settings windows can be resized. For this training CD, we will be using the drop-down menus located at the top of the window, so we can close or shrink the file and device windows to allow a larger viewing area for the settings. We must first set the real-time of day clock so that all events and waveform captures are properly time-stamped. To do this, select the Clock tab, and then double-click the Sync Relay to Computer push button. Now that the relay has been synchronized to the computer clock, let's click on the Waveform tab. The Waveform Capture function performs a high-speed capture of all three-phase motor currents, ground current, and voltages if the voltage input option has been enabled. The Waveform Capture function can be triggered on a trip, the change in state of an external input, or by the Intervista 369 setup software. Enter in the amount of the waveform record that will appear before the trigger point. This is called pre-trigger and can be from 0 to 100%. We will set it to 50%, such that 50% of the waveform capture is pre-fault and 50% is post-fault. Now let's look at the Preset tab. This tab is useful for clearing historical data resident in the 369 or to set presets for a new installation. For our application, double-click on the Clear All Data push button and save. we will now go to the System Setup menu. In the Current Sensing tab, the Phase CT Primary, Motor Full Load Current Rating, Ground Current CT are set. Phase CT Selection. The correct selection of the motor's phase CTs is critical to ensure proper relay operation. For acceptable resolution, the phase CT's primary rating should be no more than twice the motor's full load current rating and no less than the rated motor full load current. The closer the CT primary rating is to the motor full load current rating, the better the phase current resolution. From the example motor datasheets, we can see that the example's motor's full load current rating was found to be 347.5 amps. The protection engineer then selected standard 400 to 5 CTs for both the phase and ground CTs. Motor full load current setting. From the datasheets, we can see that the motor's full load current rating is 347.5 amps. Therefore, the motor full load current was set to 348 amps. Ground fault detection. If VTs are to be used, as is the case in our application, enter the VT connection type, VT ratio, and motor-rated voltage in the appropriate fields, and save. Then select the Power System tab to enter the nominal system frequency and phase sequence. Once all of this data is entered correctly, select the Save key, and then exit the CT-VT Setup menu. We will now set up the motor thermal model, which is one of the major motor protective elements. From the main menu, select Set Points, then Overload Protection. As we stated earlier in the CD, initially, we will set the minimum number of elements for our application. To take into account the extra heating due to negative sequence current, enable the unbalanced biasing by setting the field to On. From the thermal modeling section of this course, we learned that a formula based on empirical data states that K is equal to 230 divided by the per unit locked rotor current squared. From the datasheets, we note that for this motor, the locked rotor current is equal to 631%. To calculate the per unit locked rotor current, 631% is divided by 100% for a per unit value of 6.3. The K value is now calculated by dividing 230 by 6.3 squared, which equals approximately 5.8. Then 5.8 is entered into the field for the unbalanced K factor and saved. Note that the value is rounded up to 6. The hot-cold curve ratio is calculated by simply dividing the hot safe stall time by the cold safe stall time, or use the motor thermal limits curve. For this example, both are available. Using the datasheets, the hot-cold curve ratio is 16/18, which equals 0.89. The motor manufacturer indicates that the running and stopped cooling times are 30 minutes and 1 hour, respectively. From the motor thermal modeling section of this course, we learned that in order to derive the cooling time constants for the 369, we simply divide the running and stopped cooling time by 5. Therefore, values of 6 and 12 minutes are entered respectively. Since we have RTDs, we will select RTD biasing. This additional model determines the thermal capacity used based on actual measured stator temperature and acts as a backup protective element to the thermal model. The thermal model can only look at motor current and cannot account for such things as loss of cooling or unusually high ambient temperatures. This is where the RTD biasing comes in. When enabled, the RTD biasing function within the 369 uses the actual temperature measured by the RTDs and calculates the motor's thermal capacity based on a simple curve. The 369 then takes this value and compares it to the thermal capacity derived through current measurements and a motor model. Under normal circumstances, the thermal capacity calculated using the model is more precise and higher than that derived through RTD measurements and graph. Whichever value of thermal capacity is greater is the value that is used by the 369 thermal overload element. The RTD bias minimum is set to the ambient temperature the motor was designed to meet. This information is obtained from the datasheets, and in this example is 40 degrees Celsius, and so 40 degrees Celsius is entered. The center point temperature is set to the motor's hot running temperature and is calculated by taking the sum of the motor's design ambient temperature, the motor's rated temperature rise, and the hot spot temperature. For this motor, the motor's design ambient temperature is 40 degrees Celsius, the motor rise is 80 degrees Celsius, and the hot spot for our motor's Class F insulation is 10 degrees Celsius. This gives us a sum total of 130 degrees Celsius. Therefore, 130 is entered as the RDT bias midpoint. This set point is set to the maximum temperature rating of the insulation or slightly less. Our motor uses Class F insulation, which has a maximum rated temperature of 155 degrees Celsius, and so 155 is entered. Standard curve number 7 was found to be just below the cold thermal limit and above the hot thermal limit, and therefore the best fitting curve for this application. With the cursor, select the standard curve style and enter a value of 7 for the curve number as shown. From the data sheets, we note that the motor's service factor is 1.15, and so according to the theoretical portion of this course, the overload pickup could be set as high as 1.25. Owing to the fact that modern motors do not have as much extra thermal capacity as older motor designs and the application, the protection engineer has decided to set the overload to 1.1 times the motor's rated full load current. Next, we will assign the thermal capacity trip relay. The trip relay will normally energize upon a thermal overload, and so the trip relay was selected. A standard overload curve will work well for this application, but this is a good point within the course to show how to enter a custom overload curve. First, the customer obtains the hot and cold motor thermal limits curves from the manufacturer. Ideally, both the hot and cold thermal limits curves are plotted on one graph. The protection engineer then plots a custom motor thermal limits curve, which runs between the hot and cold thermal limits curves as shown. From the main menu, select Set Points, then Overload Protection, and then Overload Curve. In the Select Curve Style field, select Custom. Next, enter the custom curve into the 369 relay by entering trip times for the 30 pre-programmed multiples of the pickup level. We will now set up the additional current elements. Select the Current Elements menu, and then the Short Circuit tab. The Short Circuit Trip. The short circuit trip should be set above the maximum locked rotor current, but below the short circuit current of the fuses. To calculate the setting for the short circuit pickup, perform the following steps. Calculate the maximum locked rotor current by multiplying the motor's full load current of 347.5 amps by 631%, for a result of 2,192.725 amps. This result is then multiplied by 1.7 to raise the short circuit pickup just above the maximum theoretical asymmetrical starting current to a value of 3,727 amps. The short circuit trip pickup is set in units of the phase CT primary rating, which is 400 amps. Dividing 3,727 by 400 gives us a result of 9.31. Therefore, 9.31 is entered as the short circuit trip pickup level. Unbalanced alarm and trip. This feature is primarily used as a means of detecting the loss of one of the motor's phases. If there is little or no voltage unbalance, a setting of 10% for the unbalanced alarm with a delay of 10 seconds, and a trip setting of 25% with a delay of 5 seconds is appropriate. Ground fault. In our example, we are using a zero-sequence CT. The zero-sequence CT is checked to ensure that it wouldn't saturate under maximum ground fault conditions. Refer to the CT selection portion of the course for detail on the CT saturation calculations. The trip is set to latched. Owing to the noise immunity of the zero-sequence configuration, the ground fault trip level will initially be set to the most sensitive setting possible. We now proceed to the motor starting menu. The acceleration trip setting. In our case, across-the-line starting is used. A setting of 13 seconds would be appropriate. With this option enabled, the number of starts per hour and the time between starts can be set as per the datasheet. This may be considered backup protection to the thermal model. For our example motor, this information has not been given, and so the option should be left disabled. Enable Start Inhibit. This feature can only be enabled after 5 consecutive starts and if the load is consistent for each start. The restart block feature may be used to ensure that a certain amount of time passes between stopping a motor and restarting that motor. If, for example, a motor is driving a very high inertial load, once the supply to the motor is disconnected, the rotor may continue to turn for a long period of time as it decelerates. For a short period of time, the motor becomes a generator, and applying supply voltage out of phase may result in a catastrophic failure. In our example, we have no additional information regarding restrictions on a restart, and so this feature can be left disabled. From the Motor Start Inhibits menu, select Backspin Detection. If the backspin option is available on the 369 and required by the process, enable the element and specify a minimum permissible frequency from the formula. The minimum frequency equals the minimum speed times number of poles divided by 120. Enable the prediction algorithm and specify which output will be used to inhibit the motor start and the number of motor poles. Now that the motor starting elements have been set, select Store and then OK to return to the main menu. In the local RTD configuration menu, the RTDs connected directly to the 369 can be configured. The selections are as follows. The applications that can be assigned are None, Stator, Bearing, Ambient, or Other. A setting of None turns an individual RTD off. RTDs with the application set to Stator are used for RTD biasing of the thermal model. If an RTD application is set to Ambient, then it is used in calculating the learned cool time of the motor. We will configure the Stator RTDs, and so Stator is selected for the application. Each RTD is individually assigned an RTD type, depending on how it is connected to the input. Multiple types may be used with a single 369. We will select Platinum. Each RTD may have an 8-character name assigned to it. This name is used in alarm and trip messages. Each RTD can be programmed for separate alarm, high alarm, and trip levels. Trips are automatically stored as events. Alarms and high alarms are stored as events if the Record Alarms as Events set point for that RTD is set to Yes. From the datasheets, we can see that this motor has a Class F insulation that has a temperature rating of 155 degrees Celsius. Therefore, the Stator RTD alarms and trip are set as follows. The RTD alarm level should be set to a level that provides a warning in the event that the motor's temperature has risen above a normal level. If we take the sum of the motor's rated ambient of 40 degrees Celsius and rise of 80 degrees Celsius, plus a 10-degree hotspot allowance, we come to a maximum normal operating temperature of 130 degrees Celsius. Therefore, an appropriate setting for the alarm would be 130 degrees Celsius, while the high alarm and trip should be set to 140 and 155 degrees Celsius respectively. The trip voting feature provides added RTD trip reliability in situations where malfunction and nuisance tripping is common. If enabled, the RTD trips only if the RTD or RTDs to be voted with are also above their trip level. For example, if RTD1 is set to vote with all Stator RTDs, the 369 will only trip if RTD1 is above its trip level and any one of the other Stator RTDs is also above its own trip level. RTD voting is typically only used on Stator RTDs, and typically done between adjacent RTDs to detect hotspots. Stator RTDs can detect heating due to non-overload or current conditions, such as blocked or inadequate cooling and ventilation or high ambient temperature, as well as heating due to overload conditions. Bearing or other RTDs can detect overheating of bearings or auxiliary equipment. The remote RTD alarms and trips would be set up in a similar fashion. Once the motor RTD temperature elements have been set, save and return to the main menu. If VTs have been installed, the under and over voltage alarm and trip elements can be configured. Under and over voltage protection. The under voltage trip should be set to 90% of nameplate unless otherwise stated on the datasheets. The over voltage element should be set to 110% of the motor's nameplate unless otherwise stated in the datasheets. From the main menu, select S9 Digital Inputs from the main Setpoints menu. It is highly recommended that the spare switch input be used as a starter status contact input. A 52A or 52B breaker contact can be selected. For a normally open starter auxiliary contact, select Starter 52A. It is essential for proper operation of start inhibits such as starts per hour, time between starts, start inhibit, restart block, and backspin start inhibit. This is especially true when the motor may be run lightly or unloaded. Without an input configured as the starter status input, a motor stop condition is assumed when the motor current falls below 5% of CT primary rating. If the motor is running unloaded or idling, the 369 can initiate nuisance lockouts if the starts per hour, time between starts, start inhibit, restart block, and/or backspin start inhibit elements are enabled. When the spare switch is programmed as starter status, the 369 will detect a motor stop condition when the current falls below 5% of CT and the breaker is open, which eliminates nuisance lockouts. Select Save and then return to the main menu. Once the relay has been programmed, the settings should be saved to a file using the following procedure. In the online window, highlight the relay whose settings you want to save to a file. Select File, then Read Settings from Device. Once the settings have been read, the program will prompt you to enter a name for the settings file and optional path to save the file. Enter a name and a path, and then click on the Save button. Once the file has been saved, it will show up in the offline window. The following procedure describes how to download a setpoint file to the relay. It is essential that when downloading a complete settings file to the relay, it should be out of service. Select the settings file from the offline window. From the File menu, select Write Settings to Device. The software will warn you that the relay should not be in service. Once you acknowledge by clicking OK, the software will prompt you to select which relay by clicking on it, and then clicking on the Send button. Select the Actual Values menu. The Actual Values menu allows the user to get real-time data about the motor in addition to the event log and waveform capture tools. The Actual Data menu is divided into submenus, which we will now review. The Motor Status menu provides information about the motor, local and remote I/O alarm and trip information. The Metering menu provides real-time metering of motor currents, voltages, power, RTDs, in addition to backspin information. The Motor Learned Data menu displays information that the 369 relay has learned about the motor in the application, such as acceleration, starting current, starting capacity, running and stopped cooling times, in addition to the RTD data. The Statistical Data menu displays actual statistical data about the motor, such as running hours and trip data. Event Recorder. A record of the last 250 events is available here, along with the cause of the event and the date and time. All trips automatically trigger an event. Alarms only trigger an event if logging to the event log is enabled for that alarm. Loss or application of control power, service alarm, and emergency restart opening and closing also triggers an event. After the 250th event has been recorded, the oldest event is lost as all events move down in the event log to make room for the latest event when a new one is added. Waveform Capture. The software can retrieve waveforms that were recorded at the instant of a trip. 16 cycles can be captured, and the trigger point can be adjusted to anywhere within the set cycles under the System Setup menu. The last 3 waveform events are viewable. The waveforms that are captured are phase currents A, B, and C, ground current, and voltages AN, BN, CN if Y connected, or AB and CB if open delta connected.